This computer. All right. So exam will start from casing design, right? Or sorry, the pressure loss, right? So pressure loss is basically the drilling hydraulics. So we talked about this buoyancy force, these actual force calculations are not part of the exam, but you would need to do these kind of similar calculations for your casing design, right? So, but that's not specifically part of the exam because we had one question in the last exam from this part. So officially, practically, your exam will start from these pressure loss calculations, which is slide 24. That's where it starts, basically. So we started from drill bit pressure loss equation, and example for that, hydraulic horsepower. These were not part of previous exam, right? So the impact force calculations for the drill bit, but our main focus was mostly, we had we had the rheology because we had it in drilling fluid, so it's again repeated here. So that's part of the exam, but I will not give you a specific question about rheology. So basically your exam will have, I think, around 5 problems. There is no true false question for this exam, and all of them are problems to solve. So I think there will be 2 problems from pore pressure calculations. There will be 1 casing design and 1 or 2 problems from the hydraulics. So that's kind of will be the structure of your exam. So the problem regarding the pressure loss calculations is pretty clear, I believe. It could be either coming from the Bingham plastic fluids or it's coming from the power law fluids, right? So your homework was based on the power law fluids, right? And you did those calculations. The examples here we have both for Bingham plastic fluids and also for the power law fluids. All the equations I will give you that you would need for this exam. And basically any pressure loss calculations, if you remember, starts with the calculating the velocity, right? And once you calculate, let me go where we have everything. Maybe power law example. The general process is the same for power law fluids and Bingham plastic. The equations though are different, right? So that is what would be basically the case. And pressure drop calculations again starts with your velocity calculations, unless you would need some parameters from your rheology. For example, for power law fluids, if you are given the speed, the RPM from viscometer readings, you would need to calculate the exponent n, and you would need to calculate the consistency index before calculating the velocity. So basically, your first step is to calculate the properties of your drilling fluid in terms of rheology. Now, power law fluids are N and K, right? And for Bingham plastic, you would need to calculate the plastic viscosity and what else? The yield point, right? So that's the first step you do. Now, we had kind of discussion here that if you are calculating things in the annulus, you would need to use basically the 3 RPM and 100 RPM readings, right? To calculate those properties. And if you want to calculate the properties in the drill string inside drill pipe and drill collar, you would need to use 300 and 600 RPM data, right? So that's for the rheology. Any questions here for the rheology? That's the first step basically you do for any pressure loss calculations. So once you calculate your components n, the parameters n and k, or the rheology, then the next step is to calculate velocity, and we need velocity for what purpose? Why do we need the velocity? Anybody, any idea? Well, you need to calculate, you need to decide about your flow regime, right? If it is a laminar flow or turbulent flow, right? And in order to calculate that, you would need to calculate your velocity, right? And velocity, once you calculate it, there are equations which will be given to you. You just need to know what equation to use from the list of table of equations that you will receive. But once you calculate your velocity, you need to be careful also about the units that you put there, gallons per minute for Q, outer diameter, inches for basically the outer diameter, right? So you calculate your velocity, then you calculate your, for power law fluids, you calculate your effective viscosity, and effective viscosity using this equation, which you see there are parameters from your rheology K and N there. You see the outer diameter in that equation. And then once you calculate your effective viscosity, you can calculate your Reynolds number. Now, based on the Reynolds number, you decide if your flow is laminar or turbulent, right? So that's what you would need. And since this number is greater than 2100, which is basically the number that we use for deciding if flow is laminar or turbulent. If it's greater than 2100, then it's turbulent. If it's less, then it's laminar. You would need to use those equations that you would need for each of these flows, right? Flow equations. So for turbulent, you can calculate your friction factor using this equation, A over Reynolds number to the power of B. And A is calculated using this, B, this equation, N is the exponent N in your rheology, right? So once you calculate these two, you put it into this equation with Reynolds number, gives you the friction factor. Make sense? So once you calculate your friction factor, then you can use the pressure loss equations, which include the friction factor, and then it gives you the pressure per unit length, pressure loss, and then you multiply this number by the length of the section that you are calculating the pressure loss for, right? So that is basically the general process, and it can be applied to all the sections in your drill string system, right? Could be in the drill collar, which is written here, could be the annulus of drill collar and bell bore, annulus of drill pipe and bell bore. So you just need to make sure what diameters correctly to use. Make sure if you are given, you have a casing here, you use the inner diameter of the casing. If you don't have a casing, you use the bell bore diameter. So that's basically how you, the way you need to decide about that is to see what surface does your drilling fluid vet, right? So that's what you need to consider when you calculate these pressure loss. Well, examples here for annulus, for your drill string system, right? And another thing that we did calculate was the pump pressure. Pump pressure is basically, I think the equation is here. The pump pressure is the summation of all pressure loss within your system, right? Plus any hydrostatic pressure change. Now, since you start from the surface, go back to the surface for pump pressure calculations, this hydrostatic pressure is 0 because the level of fluid hasn't changed, right? From the inner of the drill string to the outer, to the annulus at the surface, right? So you just need to calculate all these pressure losses, add them together, and that gives you the pump pressure, right? Any questions so far?
Would we have to do the graphs like we did in the homework? Because that was really confusing.
You wouldn't need, but I very much like to clear that for you guys because some of you guys had that question as well. I will talk about it after I finish this part, but you will not need to do it in the exam, So, but I will teach you. You would need to learn that.
Thanks.
Yeah. All right. Any other questions? So the pump pressure, we also had the pressure at the points. For example, I ask you to calculate the pressure at this point, right? What is the pressure at that point? Just pressure, right? So in that case, if you are in annulus, you basically consider the hydrostatic pressure at that point, whatever length of fluid is on the top of that point, right? In the annulus, plus friction pressure loss, right? Within that section again, right? So you calculate the annulus pressure loss from the surface to the point of interest that I ask you, and you add that number to the hydrostatic pressure at that point, and that's it. That's your pressure at that point, right? It could be done for the next section. So if I ask you to do it for this section, then you calculate the total hydrostatic pressure, and then you have two pressure losses to calculate. One, the annulus of the real pipe and well bore, one, the annulus of the real collar and well bore, and add those two pressure losses to the hydrostatic pressure, total hydrostatic pressure at that point, right? So that's how you calculate the pressure. So any questions here about pressure calculations? Just make sure you understand all these, we say the pressure word a lot, right? So we have hydrostatic pressure, we have pressure at different points, we have pressure loss, right? So make sure, don't get confused all these, right? Pressure loss is due to the flow of fluid, right? And due to the friction of that fluid with the surface of your casing or well bore, basically any area that your fluid wet the surface, right? There is a friction. That friction causes the pressure of your fluid to drop, right? That's called pressure loss. And hydrostatic pressure is due to the static weight of the fluid, which is applying to that point, right? So if you are calculating the hydrostatic pressure at this point, there is this much weight of fluid on the top of that point, which is 0.05 density depths. That's the hydrostatic pressure, right? So hydrostatic is a static property, as the name implies, right? Pressure loss is a dynamic property. So if you have just fluid inside your well bore and not moving, there is no pressure loss, right? Because your fluid is not moving. So that is one thing. Another thing, and then also you have the pressure at any point, right? So that's the general pressure at any point. If you have a static system, that pressure is equal to the hydrostatic pressure. If you have a flowing system, then that pressure loss will be added to the hydrostatic pressure. That gives you the pressure at that point, okay? So just to make it more clear, hopefully. If you guys have questions as I talk, just don't hesitate to ask. So that's it. You can do the same calculations for Bingham plastic. I will give you this table of equations. Make sure you're familiar with this table. This table is in the book as well with better resolution. And the book is online in your library as well, right? So that's table 4.6, I believe. The velocity equations are there. The flow behavior parameters for Newtonian Bingham power law fluids are there. Turbulence criteria, so laminar or turbulence, pressure loss equations. So that's a full complete table that you would need for basically pressure loss calculations in the exam. Okay, so make sure you're familiar with that too. And some of the equations, if you remember here in this example, was slightly different from this table, right? So I will tell you which equations. If I will give you one set of equations. Most likely, if I give you an equation, I will use this example equation. So make sure you're familiar with the example as well. So yeah, I guess that's it for pressure loss. Also, make sure you understand the concept, right? The pump pressure, the pressure drop at the beat. I don't know, all these concepts, just make sure you're familiar with, right? Now, a couple of figures that was so confusing for everyone. One of them is this one. This is basically the friction pressure, right, at any point inside your system, okay? We didn't talk about this a lot, right? This one we didn't talk about. So if you look at here, your pump pressure is 2,100, right? That means that since your fluid starts moving from the top of your drill pipe, right? That's where your fluid start to move into the system and goes down, passes the drill bit, go up from the annulus, right? That's how it moves. That pressure, that's the initial pressure of your fluid, which pump provide that pressure, 2,103 psi, right? So initial pressure is 2,103. That's this point. That's your initial pressure of the fluid, right? Now, your fluid loses the pressure, right, as it goes down, right? How much it loses? It's based on how you calculate your pressure loss. So let's say you go to your drill pipe, right? Initially, your fluid started here, so you will lose the pressure just due to the friction here. We are talking just about the friction, not hydrostatic increase as well, right? So you will get to this point. From there to here, you have friction with the wall of the drill pipe, and you did calculate that pressure loss at the beginning of this example. And that is equal to 665 psi, right? So your pump pressure from 2000, which is started at 2000, right, drops by 615 psi. So that comes around 1500 psi, right? That's this point. So that's inside your drill pipe still, right? So that's how this line is drawn. Pump pressure, how much you lost, next point, right? Now the next section is your drill collar, right? How much you lost in your drill collar, 227 psi. So what is the length of your drill collar? Whatever length that is, the length of my drill pipe was 11,000. The length of my drill collar is probably 600 something, I believe, I don't remember, but your pressure drops by 200 to 70. So this is 200 to 70 psi drop for that specific length, right? Or maybe this is 10,500. Let me double check the lengths. 11,400 is your drill pipe. 600 is your drill collar. So it's basically drawing linear lines, right? On the x-axis is your length. On the y-axis is how much the pressure would be without considering hydrostatic, because it's just about friction. We want to see how our friction is changing, okay? So anyway, that comes here, then that's the drill collar, right? And then why do we have a significant pressure without any length change? Why is it vertical? Because there is no length change, right? Because it's due to the beat. Beat length is very small, so it doesn't really significantly changes your length, but you have significant pressure loss, and that amount is equal to 1,000 almost, 1,026. So you go from this point, 1,026 down, and that's, you end up to this point. Still the same depths because it's drill bits, right? And then you enter the annulus, right? Annulus of drill collar and well bore, right? And then you go up, right? How much you lose on that area? 32 psi. What is the length? 600 feet. So you add 600 feet to this length, and then you drop by 32 psi from that point. So you are here. And then finally, the last section here, you lose 153 psi over a 10,400, 11,400 lengths, right? So you go 11,400 and you just drop by 153 psi because that's what we calculate there. And this is the friction pressure plot. Any questions from this plot?
No, I was confused about the other one.
Sure. Okay. So great. I'll if this one is clear, then the next one will be clear, which I will describe it. Just a second. All right. So now next, you mean this one or next one? This is pretty clear.
No, the next one.
Next one, yeah. But let me talk about this one as well, because then we will combine these two together. So, all right, hydrostatic. So can any of you describe this one to me? This is hydrostatic pressure, right? So anybody can tell me how this graph is changing?
The pressure is going up because it's going down.
So where is this point?
0. Start from the surface and it's going up to the bottom hole.
Exactly.
And then when the pressure is going up, loses some pressures.
It goes up all the way to the bottom hole, right? And then from the annulus, it goes up. Since you're going up, the hydrostatic pressure drops, right? And then once it reaches to the surface, it becomes basically 0, right? Because at the surface, there is no hydrostatic pressure, right? So from here to that, whatever 12,000 feet is hydrostatic, it's linear because the mud density is constant. And then from annulus, as you go up, the weight of the fluid on any point decreases, and then until you reach to the surface. So this is annulus, this part is drill string. All right, so any questions here? All right. So next one, which you had question, right? Now, this is a static, right? Because there is no fluid movement. This blue one is a static. It means that that's the hydrostatic pressure changes, right? Now you had another graph, which was the friction pressure, right? So you need to combine these two, or that's one way of doing it, just combine these two separately, right? Or you can do something else. You can just calculate those pressures based on whatever we did calculate, right? For example, if you remember from your homework, the pressure was asked you to, I think in the homework, you were asked to calculate the pressure at 6,000 feet, 10,500 feet, several points, right? In the annulus, also in the drill pipe, right? So the first point here, this circulating one, is what? What is this point? What is this 2000 psi there?
Pump pressure.
Pump pressure, right? So you start from pump pressure because that's the surface, that's the pump pressure. So that's what you start with, right? Now, once you go down, let's say you go from, let's look at how your pressures have changed, right? From this point, surface 2000 psi, all the way to this point on the top of your drill collar inside the drill string system, right? So how what components have changed from surface to this point? You guys tell me. So what has changed from this point, which is the surface, to this point in terms of pressure?
Just depth, right?
depth has changed, exactly. So once depth changes, right, what pressure are we talking about when you have a change in depth? Which of those? What's that? Hydrostatic, right? Depth change. There are static properties, static pressure change, and there is a dynamic pressure change. So the static one is hydrostatic, right? How much it has changed from the surface to that point. Is it increased or decreased?
Increased.
Increased, right? Exactly. So increased by how much? By 0.052 multiplied by the depth multiplied by the density, right? And you already saw that in this figure, right? So from here all the way maybe to some point 11,000 something. This is how much your hydrostatic pressure, around 7,000 psi probably, right? So your 2,000 psi have increased by around 7,000 psi to around 9,000 feet. But is that the only pressure that we should consider here when circulating? Is that the only pressure that basically... Now, let me ask you one question here. This line, the blue one, and this purple one, are they parallel to each other? Do you guys think they are parallel? Do you see them parallel?
What was that doing?
What's that?
I don't think they are.
Okay. Anybody else? Anybody think that these two lines are parallel?
With the circulating, I don't remember this that well because this homework was quite a while ago. But wouldn't it be parallel because it's just the pump pressure plus the hydrostatic?
Well, that's a good question. When you circulate, do you have any pressure loss when you're circulating?
Yes.
Due to friction, right? And all these pressure losses that we calculate because of circulation and friction of your fluid with the walls that basically touches, right? So we have a friction loss in addition to the change in hydrostatic pressure, right? So the reason that these two lines are not parallel to each other, you look at the zero depths, it's from 0 to 2000 psi. If they were parallel, here you also should have around 2000 psi difference, right? But how much is it? It's probably, it's definitely less than 2000 psi, right? So these two lines approached each other, right? Due to friction, right? So whatever the difference is, at any point that you calculate that, you should consider the friction as well. So you lose some pressure, right? So hydrostatic pressure increases. Let me see if I can draw here because that helps me describe this. Edit PDF, maybe. Oh, well, none of these options are open. Edit, add text, add image, link, add footer, what's text? Okay, now it's activated, but it's just the text, so nothing else. Well, I can't apparently.
I just remember I had the whole graph, right? Except for, I know for a fact, me and Eric kind of worked on this one together. We did not really understand that very tip point of the purple curve.
Yeah, here.
Yeah, that's where we got stuck. Everything else we were all good on.
Okay, so I'm gonna show you here. I remember that I can use Zoom also to draw things. So let's assume that this line that I'm drawing, which is not going to be, but it is, let's say it's parallel to that line. This is the parallel line. This is the actual line that is happening. The difference at any point, the difference between this point at any depth and that point is due to pressure loss. So this is how much you have pressure loss at depth 6,500, let's say. Okay, so what you need to do is to calculate at any point, just a summary here. At any depths, you need to calculate your hydrostatic pressure, right? So let me look at 5,000 PSI. This is your hydrostatic pressure, right? And you would add basically your pump pressure, of course, right? How much is your pump pressure? 2,000. Sorry, I thought this is the depths, but I should go vertically. So this is not correct. And that was correct. Yeah. So draw lines. I can draw lines. Yes. Cool. All right, sorry guys, I'm taking your time, but I think it's important to understand this part. So let's say at one specific depth that you want to calculate, right? And then draw just line here. All right, so let's look at 10,000 feet, right? So you calculate your hydrostatic pressure at 10,000 feet, which is going to be this number, right? And then you add the pump pressure to that, because pump pressure plus hydrostatic is going to be the pressure at any point if there was no friction loss, right? So you go up to this point, right? So from whatever 6,500 to 8,500 PSI, right? And then you calculate your pressure loss at that section and subtract from that pressure. So basically your equation becomes at any point of this line at any depths will be your hydrostatic pressure plus your pump pressure minus your friction pressure loss. Sorry for my handwriting. This is going to be this pressure that you see at any point. Does it make sense?
Yep.
Hydrostatic plus the pump, which is exerting that pressure at the surface, minus the pressure loss. So it gives you that purple line. Now here the tip is due to the drill collar. So up to this point is drill string. From this point to this point is your drill collar. So this length, this small length is your drill collar length. That's why you see it's changed, because the pressure loss inside your drill collar is different, right? It doesn't change with the same rate. The rate of change of pressure loss inside the drill collar is different from your drill pipe, right? So that's why you see it's kind of the tip is different, right? And then once it goes down, here is due to what? Anybody? Why does it go down without changing any depths?
Because it's such a small depth, like it.
That's a huge change in a small depth. What is that? Which area inside your wellbore have that property? Bit, right? This is the pressure loss inside your bit. So drill pipe, drill collar, bit, then you enter your annulus of drill collar, which is a very small section. You don't see really any significant change. Probably it's somewhere here, but you don't see it really. And then you continue all the way to the surface. Now, one important point. This is for your drill pipe when you are inside, but when you are inside the annulus, the pressure loss will be added to your hydrostatic. So this is when you only are in drill pipe, pressure is equal to friction plus hydrostatic. That's it. You don't consider the pump. Why do we not consider the pump? Because this friction pressure loss is calculated from the surface. So let me go up. Because we calculate the pressure loss at any point inside the annulus by considering what? From the surface to this point, right? So this is the pressure loss. This is the hydrostatic, and pressure at the surface of the annulus is 0. Pressure at the surface of the drill pipe is 2000, is pump pressure. That's why you have the pump pressure there, but you don't have it in the annulus. And that's the difference between annulus. So this is for your annulus here, this equation. This is for your inner drill string. And that is how you calculate that. So I think I was in this slide somehow. I put it on the screen, but anyway. I hope it helped. Any questions here?
Now I get it. Now.
All right. So if it's still confusing, it's okay. You can come to my office hours and ask. It's okay. It's not very straightforward for sure. It's a bit confusing. So, all right. So let's continue quickly. So one question from here, one or two questions from this part, right? How can I clean my screen? Annotate, clear. All right. Okay, cool. And I'm going to delete this. All right. So let's go to casing design. Casing design, you guys already know, right? What type of question you should expect. It's pretty clear. I ask you to design a casing, right? Very similar to this example. So if you know how to do this example, you're good to go. That's it. Okay. So if you know how to do this example or homework that I sent, homework is 3 weights. I'm not going to give you 3 weights in the exam. Probably I will give you 2 weights for the exam. Okay, so if you can do 2 weights, which is this example, you are good to go. Done. Okay, have you guys started working? I know some of you have started working on the homework.
What do you exactly mean by 3 weights? Like,
yeah. So the good question. So if you go to API 5, if you go to the casing tables, for example. Casing tables, and let's say you want to design, I don't know, this 13, and you want to use P100, right? Let's say this is your casing, right? Now, how many casings do you see here, which are 13.375 P110? 1, 2, 3, 4, 5, 6, 7, 8 casings, right? Now, you calculate your burst pressure requirement, and then you will see that, well, all of these casings will satisfy my burst requirement, right? So you need to have 3 weights inside your system. I think if you go to the slides as well, let me show the slides, casing design, slides. At the end of this example, there is this is the 3-weight design. 1 weight, an AD, another weight, 2 weights, and then 3 weights. So this is a 3-weight design. So there are 3 casing weights that would satisfy burst, collapse, tension requirements for your casing. So how do you do that? You first design for 2 weights completely. You design a 2-weight casing system, you complete that design, right? And then you go to the last, another weight, which is basically lower weight, of course, right, for the surface. And then based on that, you design your collapse to see at what depths can you set this last casing based on its collapse requirement. Okay, exact same method for the second weight, you do it for the 3rd weight. But this time you use the properties of the weight number 3. Especially you will see for P100, this homework that you're doing, there are 3 weights that fits exactly into your burst requirement. And those 3, more than 3 actually, there are 4 weights, but you want to design for most economical, so you design for the lightest of those 3. You ignore the, what casing size are we talking about here? for the homework. Pressure, homework design.
I just saw it in that folder. It was there.
Oh, you just saw it?
Yeah.
Okay.
It's like towards the very bottom. You see right above axial tension.
Here, just go further probably.
No, the extra point homework.
Ah, yeah, that's the one.
Yeah.
Thanks. Thank you. Yeah, I just missed it. All right. So, where is that? That was your exam. So,
Dr. Mo.
yes.
I know the homework is due Friday. Is there any way I can turn it in Saturday? I don't really have time.
I will extend the deadline to Sunday, so
Okay.
you guys have more time to do that. So yeah, so this is a 5.5 inch P110, right? So you go to the casing tables, P110, 5.5 inch. 5.5 inch is probably all the way. Here is the 5 and then 5.5 inch, and then P100 is one of the basically casings with high strengths, right? So you see here, and there are 3. You see these are the joint types in that table. Ignore the joint types here because you see also their properties are the same. All the properties are the same for these 3 casings. So this is 17 pound per feet. Then you have a 20. And you have a 23, and then you have a 26.
What is the? I got a question about that. Can you go
Sure.
up? Like, if you go like to the 23, what is the cross section area for a 23?
Well, you can see it here. Here is the area for 23. That's 6.63. Now for P110, sorry, I should go to P110 here. And this is P110, 23, 5.5 inch. The D over T ratio is 13.25. Pipe area is 6.63. Burst requirement or internal yield pressure is 14,000 for this specific weight. 12,000 for this one. No, sorry. That's 23 still. 12,640 for 20. So you check your burst requirement, and for example, your burst requirement becomes a number, let's say 10,500, right? And then if it's 10,500, then you see that 17 works for sure, and the rest as well will work, right? So you have multiple options, right? So you start from the heaviest, you say, okay, I assume the whole basically wellbore is filled with that casing, right? It's basically same weight casing all the way to the surface. And then you see, okay, this is not economical. I'm gonna add another casing. I use 20, right? So 23 at the bottom, 20 at the top. Now, what depth should I set 20? You use the exact method that we discussed here to set the depths, right? And this is exact method. You collapse pressure divided by design factor, find the depths, fix for axial tension, decide what type of collapse you have, calculate a new collapse rating. Once you calculate collapse rating, then calculate the depths again, do the iterations, right? So you do the iteration, you set that depths. Now you have a 23 to some specific depth. Then you have 20 all the way to the surface, right? Then you say, this is not the most economical still because I can use 17 as well, right? So you go back here, and instead of using the collapse pressure for 20 in these equations, you use the collapse pressure equation for 17, right? So you put 17 here, and you do all these process again, all these process until your iteration doesn't change your feet height anymore. And that's it, you're done. The only thing is that you need to consider is that when you calculate the axial tension on 17 pound per feet, you have 2 pieces of pipe. One is 23 pound per feet, one is 20. right? For the tension calculations, on the lowest weight, you have two pieces of pipe being attached to the final weight. One is 20, one is 23. So you calculate that weight. And of course, you have to use the cross-sectional area of 17 when you do that type of calculations, this pipe, right? So make sure you follow the example. For the exam, just make sure you know how to do the two weight. 3 weight is practically the same as 2 weight. You just add one more weight to the top. And same exact method you follow, right? If you have questions, I'll be in my office hours. Just don't hesitate to come and ask me. But if you're familiar with this example, you're good to go for the exam. You can easily solve the problem. Okay. If you guys have any question from casing design, you can ask now.
So how many questions are going to be from like each PowerPoint?
So I'm telling you what questions are coming, right? So probably you will have one question from pressure loss. That's what I haven't completely designed the exam, but probably you will have one question from pressure loss calculations, one problem, one question from casing design. It's a casing design, right? Exactly same as this example, just the numbers will change. So that's the next problem. And it's likely that you will have 2 from pore pressure, okay? Pore pressure is easiest part. That's why you see 2 questions from there, because it's easy. I decided to have 2 questions, but just make sure you understand the abnormal pressure, right? And what is the, you don't have any question for casing set depths or anything like that. That's what you do for your project. But what you need to do is to understand the concept of the pore pressure, right? What causes the, for example, look at these examples and look at how abnormal pore pressure happens, right? And make sure you understand those concepts. For example, here you have casing leaks. What happens if you have a casing leaks? The pressure here will be equal to there, right? These type of things, make sure you understand. In terms of solving the problems, you have basically Eaton's method that we discussed, right? This equation here. Make sure you understand this equation. It's pretty straightforward, right? You will be given some sort of graph like this, right? And I'll ask you to calculate the abnormal pore pressure at some specific depths. You will be given overburden, normal pressure gradient. You'll find these 2 numbers, and that's it. You have your pore pressure, right? So it's pretty straightforward to calculate the pore pressure as well. Now I could give you any of these graphs: resistivity, conductivity, sonic density. The exponents are different, you see, right? But the equation is basically the same equation. And I think that's it. That's 4 problems for your exam. I don't think I'll give you more than 4 problems.
Okay, and you said there wasn't going to be any like true or false or anything like that on this one?
No, yeah, not on this one. It's just problem solving, 4 problems, and you know what problems they are, right? So just make sure you know the examples, homeworks you did, right? And you'll be fine.
Okay, nice.
Any other questions? Nope. All right, so if there are no questions, that's it. And I'll be in my office hours Thursday and Friday as well, and Monday. So if you guys have any questions, don't hesitate to ask. I'm gonna stop this recording. Should be able to stop it here.